t comma x are linearly independent vectors. So we should have two real eigenvalue. Now, if it has two real eigenvalue, then we need to check whether it has two linearly independent eigenvector or not. If it has two linearly independent eigenvector, then we will say that this is hyperbolic. Another, we will say that it is not hyperbolic. It falls in the category of weakly hyperbolic. And in the strict partial differential equation, we don't take weakly hyperbolic as hyperbolic because it does not give us the solution in the whole domain. It does not give us the whole solution, so that's why it is not very well acceptable. So if it is not hyperbolic, then we say that it is not hyperbolic. This is more research topic. I just gave you the definition because you are the future researcher. So just write this system as rho t plus rho x u plus rho ux equals to 0. I'm assuming that the solution is smooth, so we can break this conservation form. And rho t u plus rho ut plus 2 rho u ux plus u square rho x equals to 0. Now rho t from here, you take u common plus break it into form rho u ux plus rho u ux. Bring one here. So rho t plus, I have taken rho outside, so rho ux plus u rho x, and the second form is rho ut plus rho u ux. If we use this equation first, so this becomes 0. So we are left with rho ut plus rho ux equals to 0. Now write it in the matrix form. So what are your dependent variable? Del rho over del t, del u over del t. Plus this matrix will come, say this is matrix A, del rho over del x, del u over del x is equals to 0 vector. So I am just trying to express in this form ut plus aux equals to 0. Now just pay attention to the matrix A. If we see equation number first, then the coefficient of rho x is u, the coefficient of ux is rho, and if we pay attention to the second equation, then the coefficient of rho x is 0 and the coefficient of ux is just divide it by rho because rho is common, so ut plus ux equals to 0 u. Now you can see that the matrix A is an upper diagonal matrix. The matrix A is an upper diagonal matrix. Upper diagonal, or one most important thing to check the geometric multiplicity of a 2 cross 2 matrix is that if it is an upper diagonal matrix, then all the non-diagonal elements should be 0. But here, the non-diagonal element is rho, that is non-zero. So it has two eigenvalues, lambda 1 equals to u and lambda 2 equals to u. Both are real because both are the velocity of the gases, velocity of the gas particles. Now, if we check the eigenvectors, we have
You just have like one eigenvector, right?
exactly. So it has only one eigenvector because the geometric multiplicity of this eigenvalue is 1 because of the appearance of this row on the off diagonal. So it is making only one eigenvector. Let me write it in the form.
And that doesn't span R2.
Yeah, and only one eigenvector will not generate R2. Generate R2 because this is coming from the R2. It means we don't have the facility of two linearly independent eigenvector. We do not have the facility of two linearly independent eigenvector. Okay. eigenvector. So which implies the system is not hyperbolic, or you can say that it is weakly hyperbolic. Why we say weakly hyperbolic? Because at least we have the real eigenvalues, but for the hyperbolicity, we should have n linearly independent eigenvector when the dependent variable belongs to the n space. Okay, space of n dimension. So when the dependent variable are coming from the space of n dimension, in that case we should have the facility of n linearly independent eigenvector, but that is not the case here. So this was the reason, and for we discuss, I think, p system. We discuss the p system, is not it, to discuss this thing. Yeah, next we are coming to the second question.
Um, I I just wanted to ask if the trick in the first in the 1A problem was taking the the differential of
Sorry.
a sum and how do you say the subtraction of x minus c and x plus c.
Are you talking about the first A question? So
Yeah,
so which method, like in the characteristic method, I have told you to form whether Lagrange's method, or you can simply write dx over d eta is equals to u, dy over d eta equals to y, and du over d eta equals to x. Now, if we are going to solve these things, so
but
first,
you have to check that the Jacobian of xs and xt is different than zero, right? Like to have even to have like a characteristic that passes through that point.
so the Jacobian of x equals to xi, y equals to 1, and u equals to 2 xi. So this is the xi curve, gamma curve, and this is basically the change in eta, and this is change in xi. So Jacobian at eta equals to 0, like at any point p, should be non-zero. So that was the condition which we have to check. So firstly you will solve dy over d xi equals to y, and then you will get the form of y, and then you have to use the initial condition to calculate y, and then I think you have to club these two equations to solve u and x, and then you have to use the initial condition at x equals to xi, u equals to 2 xi.
Yes.
Then you will get the form, and then you will check the Jacobian, and then you will transform from xi eta to xy for u. Like
Yeah.
I haven't seen all of your exam solution, but I am expecting that this is I think correct. I just take a look at the Camilo exam because it's submitted very soon, so that was correct. And after that, I haven't seen. I will check the question paper at the weekend when I check your assignment. Okay, so this was the thing. Next, let's talk about the question number 2.
That was pretty rough.
Sorry,
That was pretty rough for me.
rough or tough?
Tough, both.
So x is belonging to R and t is belonging to R plus. So t comma x is coming from R plus cross R. And u is belonging to R. So this is your scalar conservation now. I am going to check the point where it is convex, and then I am going to solve. Like, you have to check, you will take f dash u equals to 0 and then calculate the point of minima and maxima, and then you will calculate f double dash u. If it has if it has two maxima and in between minima is not coming, then I will just choose that one. So I think the point 0 is 0 is, I think 0 is minima. Let's see. And since you guys were giving your exams in laptop, so you could use any plotting system to check whether it is convex or concave.
What I did was just like um, take the derivative, the second derivative of that expression, and then I search for points that are greater than 0 and less than 0, and that's like I know that for the points that are less than 0, you will have like a concave function. So you will have a continuous solution because you have decreasing initial conditions.
You are sitting in the library, it has written that you should be silent.
Huh?
You are sitting in the library, it has written that you should be silent.
Oh, there's nobody else here, like usually.
I was
So,
reading the behind you silence, you know.
oh yeah, yeah. Maybe I'm doing not so good. Uh,
So, like as per my understanding, this quantity is always positive. This quantity is always positive. So, if I am able to make this one also positive, then I can say that f dash u is greater than 0. So, let's talk about that. Suppose you are taking u greater than 0, then 13.2 u minus 12 greater than 0, since both have the same sign. In that case, 13.2 u is greater than 12, or u is greater than 12 over 13.2. You can calculate this, and for the case, since this is a positive quantity, for the case u is greater than 120 over 132, this function will always be convex. Now comes to the negative part. If u is less than 0 and this function also becomes less than 0, then the whole function will be positive. Is not it? If this u is negative and this also becomes negative, so negative cross negative is positive and 2 is always positive. So u is less than 0, it means 13.2 u minus 12 is less than 0, it means u is less than 12 upon 13.2. So this quantity is a positive quantity and u should be less than 0. So in the condition when u is strictly less than 0, we don't need to focus on this one, because just let me draw it on the curve. So this is your u and this is function of u. So 12 over 13, so it should be something here. This point should be something here. So in this region, this is concave. Camilo, you are plotting the same now, like in the small region.
Sorry?
You were plotting the same, and you were getting the region that was in between 12 upon 13.2 and 0.
For u less than 0 is convex.
Yeah, and
For
and there was this interval you are getting that is giving it concave, I think.
is around 0.7 around.
Yeah, exactly. So 0.7 to 0.9, I think. So this interval is going to give you concave, and beyond that it is again coming to be convex. So I told you, I was giving you a hint that just go for the region which is easier to discuss the convexity. If you could go for the region u less than 0, then everything was very smooth for all of you, is not it? So that's what I was trying to say. So this was the case, like I formulated this question, but I did not go in the details. So this was the case, and you are going to convex function here u less than 0. So you could discuss the solution only in u less than 0, and you don't need to go for the rest, because since I already give you the discontinuous initial data, so and the initial data is monotonically decreasing. So if U is concave and it is initially decreasing, so you are going to get a smooth solution. But it is very difficult to find out the reason of concavity. So for me, it was very easy to find out the reason of convexity, because your syllabus is moving around convex function, is not it? It is written in your syllabus that existence and uniqueness to the Riemann problem for convex flows. So that's why I was asking the unique entropy solution. So if you go for the convex entropy function only, so you have to take u less than 0. And since for the convex flux function, let me write, I think then it will be very clear. For the convex flux function, if the initial data is monotonically decreasing, then we have a smooth solution.
No.
Then we have discontinuous solution, and it is very easy to find out the range for the discontinuous solution. So the solution will be like 1 comma 0, x less than or equals to s, t, s is the shock velocity, x is greater than s of t. I already gave a theorem where I wrote this. If you are able to calculate the shock velocity s, then in the region x less than or equals to s, t, it is 1, and in the region x greater than t, it is 0. Let me show you. So x less not equals to, this is the, oh, my camera is off, and it is something with my computer and I am unable to show, sorry. Okay, I cannot do anything. Okay, so 1 and 0. So x less than st and x greater than st. I think I can show this with my. So this was the case. Do you remember about that? This is in your syllabus.
Yeah.
Yeah. So it was very easy to discuss this question. Very, very easy. Like you could mention that we are going to discuss only in u is less than 0. And you guys are intelligent enough. So, okay, don't worry about that. Next, we are going to, now if you have any doubt from the unit 1st and unit 2, then please do ask, and then I'm going to proceed with the rest of the unit 3.
So we had this solution just in the region of discontinuity.
Just in the reason.
Yes, in the region where f the flux law was convex.
Yeah, so you have two reasons. Like you could simply mention that we are going to talk about the solution when u is strictly less than 0 or when u is strictly greater than 12 over 13.2. In both the regions, we are going to get the discontinuous solution and how will be the form of the solution. So the solution will be 1 comma 0. What was the right kind Huniot condition? Would anyone tell me please?
1/10, I think.
1 over
10.
10. So
Yes.
x is less than t over 10 and x is greater than t over 10. Is not it?
Yes.
So this is the entropy condition, entropy solution of for a problem. There are two
I
ways.
just
Sorry.
I just put that.
Yeah, so there are two ways to use entropy condition. Either you can use f dash ul is greater than s is greater than f dash ur to find out the entropy solution. Or simply I have given a formula to all of you. Just use that formula and put it in the entropy form. Okay. Next, we were discussing the method to solve the Laplace equation using the separation of variable. Now, today I am going to tell you what is the reason behind this method, separation of variable, why we are using this method, specifically method of separation of variable. So, I am going to give you an example and I will discard that sometimes this method works and sometimes this method does not work. So, in what case this method works and in what case it doesn't work. So, we are going to see that and we will analyze with the help of the initial condition or boundary condition. I would like to ask you in between, I will take the opportunity to ask you, are you guys available on this Thursday from 3 to 4:30? Camilo, Rebecca, Roberto, Ricardo.
Yeah, I can.
Yo no puedo el jueves.
No?
Le dije en español.
This okay. Roberto, Ricardo, because I cancelled your last Wednesday class, so I wanted to reschedule it for this Thursday, and in that way, we will be able to finish the half of Unit 3. So, if you are available, like I think everyone is available, so I am going to reschedule a class on the Thursday from 3 to 4:30, so we can discuss this is the reschedulement of schedule of previous Wednesday class. Okay, so I will also put it in the classroom, but I just wanted to confirm. So, did anyone try the method which I told you, like method of separation of variable as your homework?
Yes, and we arrived to the spherical harmonics.
We arrived.
Huh?
What are you saying? I did not get.
Yes, that we get the spherical harmonics.
Spherical.
Harmonics. Yes.
Okay. So you solve the whole problem, like you get the function solution in the form of the sine x and sine hyperbolic x. No.
No, we get Legendre polynomials.
Okay. So let's discuss. I think everyone haven't solved. We are going to solve this problem. This is the most important problem. So we are using the Dirichlet boundary condition. Like the condition is on only the boundary, not it's the derivative. And we are writing the Laplacian equation. So the Laplacian equation in two dimension, right? Uxx plus uyy equals to 0 for the region x comma y lying between 0 to pi. So they say this is your equation number first, and we are using the boundary condition. So we know that we have three kind of boundary condition. One, Dirichlet boundary condition, that is of our interest. We are not interested in any of the other. So we have three boundary condition: Dirichlet boundary condition, Newman boundary condition, and Robinson boundary condition. So this one use only the condition on the dependent variable, only the boundary condition on the dependent variable. Newman one use the boundary condition on the normal derivative of the dependent variable. However, Robinson use the boundary condition on the dependent variable as well as on the boundary of the on the derivative, normal derivative of the dependent variable. So I am repeating these things several times because someone can ask even in some viva what is the difference between these three boundary conditions. So always keep in your mind. And Newman boundary condition is used on a very broad level. So see, the boundary is from 0 to pi. Say this pi is L. For so y I'm writing y in the upper one and x in the upper one. So it is very clear here x is fixed and the variation is on y. So that's why the variation is on y. And however in the second one y is fixed and the variation is on only x. So what kind of boundary condition it is? Rebecca, what kind of boundary condition it is? She's not there. Ricardo, what kind of boundary condition it is?
What kind of condition it is? That's version of. I don't know.
Okay, so I'm repeating.
When you have like a boundary condition that it's valued on 0, then it's a Cauchy condition, isn't it?
That is not boundary condition, that is initial condition.
Initial condition. Yes.
So it has boundary.
This is Dirichlet.
Dirichlet. So again I am going to repeat because it should be very clear to you. It might be possible that in sometimes in the exam I can ask you, not me in your general exams, that one can ask you which kind of boundary condition is. It is a very good question. Most of the people ask because this is the very basic question. So initial condition is like u0 comma x at t equals to 0. So when the initial condition is sufficiently smooth, it calls Cauchy problem. When it has a single discontinuity, then it called Riemann problem. So that is not our case because we are very far away from the initial condition. The unit second was based on the initial condition. Unit third is based on the boundary condition. So just pay attention. Dirichlet boundary condition. If the boundary condition is defined only on the derivative, only on the dependent variable, if the boundary condition is defined only on the dependent variable like u a comma x and equals to some z of x and u a comma y, x comma b equals to some f of y. So we can see that here the boundary condition is defined only on the derivative. It is not involving only on the dependent variable. It is not involving any of its derivative. So is it involving any of the derivative of u?
No.
It means that it is a Dirichlet boundary condition. However, in Newman boundary condition, the boundary condition is defined only for the derivative of the dependent variable, the normal derivative of the dependent variable. In that case, this is the Newman boundary condition. The third one, that was Robinson. This is the combination of both of these. It should have the derivative and also the dependent variable. If it loses any of the condition, then that belongs to the category of Newman or Dirichlet. This is the very important thing which you need to keep in your mind. Please. So firstly, we will use method of separation of variable to solve this problem, and then we will see why we only use the method of separation of variable most of the time. We don't use any other method. So we will also see the beauty of the method of separation of variable and from where we get the idea to use this method of separation of variable, because if you are using something, then you should know what is the idea behind that. So when we are in the first order PDE, if you guys remember, when we are dealing with the first order PDE, then we have sufficient method to solve a first order PDE, is not it? We have Lagrange's method, that is, we have method of characteristics. If it is non-linear, then we have Charpit method, or we have Cauchy method of characteristic, But however,
the Cauchy method of characteristics, it's different to the method of characteristics in what sense?
yeah, so when we have a non-linear first order partial differential equation, in that case the solution surface is not a surface but it is a Monge curve. It is enveloping a Monge curve. So that's why we form 5 equations to use the. I always give the geometrical interpretation. So there was geometrical interpretation because of the non-linearity of this thing. Dx over ds equals to some non-linear function of u. dy over ds equals to some non-linear function of x, y, u.
So you have to construct the Monge cone that it's tangent to that point, right? To that strip.
Yeah. So because of that, we have 3 methods. However, when we comes in the category of the second order partial differential equation or higher order partial differential equation, we still processing with the solution, because even the partial differential equation is very simple. It is very difficult to find out the solution. Even if you have a very simple partial differential equation, ut plus aux equals to 0, then you get the solution using the method of characteristic. But as soon as it becomes like this, the solution is no more smooth in the finite domain under some initial condition. And if the problem is this, then it is very difficult to find out the solution, because we have to use the method of Cauchy method of characteristic, and it is not that much easy as it seems with its name. So when we come to second order partial differential equation, so we have some choices. Would anyone tell me what if we have a second order linear second order partial differential equation? So how we can proceed? We have that I am mentioning a linear second order PDE. Any idea?
Can we convert it to n cross 2, 2 cross 2 system of first order partial differential equations?
Exactly. So if we have a linear second order partial differential equation, so using the theory of ordinary differential equation, every nth order linear ordinary differential equation can be written in n cross n system of first order differential equation. In the same way, every nth order linear partial differential equation can be written as linear PDE can be written as n cross n system of first order PDE. So this is a way, this is linear, is not it? So using the same theory, you can write it in the 2 cross 2 first order PDE, but that is not the case. We are interested. This is a way to proceed. So it is very difficult in itself to find out the solution of a second order PDE. So we came across the method of separation of variable. I would like to say that in the notes, I only provide the bookish thing. I cannot write each and everything in my notes. So if you are attending the class, then you are going to get a lot of things like that. So where G?
I just want to make like a comment from some researchers that some researchers that were like doing a discussion about methods to solve PDE. They were like saying that, oh, it's a shame that all of the students, undergraduate and graduate students, just when they have like a second order PDE, they always use like separation of variables or something like that. I don't remember like the.
Yeah, so I am going to tell you the theory behind the separation of, that is the main point, why we are using the separation of variable.
Yeah, but the thing I wanted to say is like, oh, it's a shame that they only know separation of variables because that method doesn't work like for all of the broader problems that are in the area.
So they have to have the homogeneous boundary condition. They have to have the homogeneous boundary condition. In what sense I am talking about the homogeneity? That is the next point after the discussion of the solution of this problem. Because if we don't have the boundary condition of this type, we will not be able to use the method of separation of variable. So there is a reason why we are using the method of separation of variable, and I will give you a geometry and I will explain with the help of the geometry why we are using this PDE course is more about geometry, I think, at some point. So we are going to see why we are using only the method of separation of variable, why we are not using it like writing it in a, you can write it in this 2 cross 2 system of PDE, and then you can use the method of characteristic, which I have told you, like dx over dt equals to lambda I, and then you can proceed. But that is another case. Sometimes it is not always possible to write the solution, only we can discuss its stability and all, how we did in ordinary differential equation. But that is the another thing. Now z is a continuous function satisfying z 0 equals to 0, g pi equals to 5. So why this is so? Since we have the initial condition u 0 comma y equals to 0. And if we u x comma pi is equals to g of x, so according to this u 0 comma pi should be 0. So that is basically z of 0. So this is because of the continuity of the function. And the next condition u x comma pi equals to 0. So u pi comma pi should be 0 according to this condition, and that is equals to g pi. So this is the coming because of the continuity of the function. This is where this is understood. So that's what I was saying, that everything is not written in your notes. So here, if we assume I am going to give you the solution of the same PDE that cannot be written in the method of separation of variable, and that will also satisfy. That will also be the solution of the PDE. Suppose we have the solution of this PDE in such a way that it can be written as a separate function of x and separate function of y, that it can be written as the product of two functions, and two functions are like such that one is separate function of x solely depending on x and the second one is solely depending on y. Then substitution of this PDE, then substitution of this function in the first equation will give the derivative is your task, it is not mine. So x double dash y plus y double dash x equals to 0, or we can write it like that, x double dash over x equals to minus y double dash over y. Suppose this is equals to some lambda, then x double dash plus lambda x equals to 0 and y double dash plus lambda y equals to 0. It is not a plus, it is a minus. Oops. Now the characteristic of this ordinary differential equation is this. So m equals to plus minus iota lambda. So x equals to c1. Let me check the coefficients which I am using. I haven't used the Legendre polynomial. I don't know why you are using the Legendre polynomial. A.
Because you are solving it in rectangular coordinates.
Sorry.
Because this way of solving it is in rectangular coordinates.
Okay. Now.
I solved it in like a spherical coordinates.
Ah, okay. So we have a boundary condition u 0 comma y equals to 0 is equals to u pi comma y. Since y is fixed here, only the condition on x, so that's why we are considering the first condition. As soon as you take u 0 comma y equals to 0, this will be 0 is equals to a into 0 plus b into 1. So b equals to 0. And as soon as you use the condition u pi comma y equals to 0, so 0 equals to a sine pi pi lambda, and which gives the lambda should be of the form n square, because only on the integer this is going to give us the 0 value. So we get the solution like x and x equals to a. Write here n as well. Is it clear how I am writing the solution? So square root of lambda will be n here.
This equation is used like for a vibration of a membrane, right?
I don't remember about the vibration of the membrane, so I won't like to go there, sorry. Now this lambda equals to n square. So it has a two way to write. Either the characteristic is this, then m equals to plus minus n, and we can write the solution like e n. This is function of y, e and y plus constant like cd, c dn, or you have another way to write it in the hyperbolic function, sine hyperbolic and cos hyperbolic, because we know that exponential function and hyperbolic function are same, is not it? So I am using the hyperbolic function, and there is a reason behind that, because we are using this sine function. So sine function like sine x, so we are going to use the form of sine hyperbolic and cos hyperbolic, so that they will be in the same resemblance, like they will look alike same. So that is the reason I am writing in the sine form. Some of the author also write the solution like this. So don't get confused with those things, okay? So the solution will be y and y equals to dn sine hyperbolic and y plus cn Actually, I have used the BN coefficient 2 times in my notes, so that's why I try to manage it here. Again, you need to use the boundary condition u in which x is fixed. So one condition is u of x comma 0 equals to 0. As soon as you will use this condition, you will get this Cn is equals to 0. Because this will be non-zero, so Cn have to 0. So we are left with so we have this form. Hence the solution is product of this, and n is varying from 1 to infinity, and n is being integer. So that's why n is can be written in the form of summation. So ux comma y equals to summation n varying from 1 to infinite an dn sine nx sine hyperbolic ny. Suppose this is a fixed constant, say an. So this becomes u which is satisfying the 3-0 boundary condition. You can check, and the fourth boundary condition which is at y equals to pi now gives you x comma pi. Say this is your equation number second, and equation number first is this. No 1 2, this is third, and this is your equation number fourth. So ux comma pi is equals to summation n varying from 1 to infinite an sine nx sine hyperbolic and pi is equals to g of x. But since g is continuous with g0 is 0 and g pi is equals to pi, so we can use the Fourier sine series sine series. So because of the continuity of this g, the Fourier sine series converted absolutely and uniformly to g, and so the coefficients an can be obtained as an sine hyperbolic and pi. So this is a constant for this series. Only the function is function of x. So this is equals to 2 over the
Because the function is it's odd, right?
sorry.
The function is odd, so well, you have that too if the function you will have that too if the function was
I'm not getting what you are asking. Could you please repeat in a clear way?
nothing. Everything's all right. Sorry.
Okay, so this solution u with this constraint is the solution of the wave equation. Is the solution of the Laplace equation, sorry. This solution 4, equation number 4 with constant 5, because 5 is used to calculate this coefficient. Equation 4 with constant 5. You can say constraint, or you can say an extra condition with constant 5 is the solution of the given Laplace equation with Dirichlet boundary condition. Now, our next thing, why we are using the method of separation of variables. So let's talk about that. If you guys have any doubts till this, then you can ask. Another we are going to. Okay, just I am writing an example. This was the PD into D na Laplace equation which I had written earlier. This was the Laplace equation in 2 dimension, is not it? So I am saying that please let me know whether this is the solution of the given Laplace equation or not. Please let me know about that. I am saying that this is a solution of this Laplace equation. Please check it and tell me.
Yes, it is.
It is. So you can see that. And is it in the form x, x, y, y? No, it is not in the form of x, x, y, y. And if I take the boundary condition u 0, comma y is equals to some function of y and u x comma 0 equals to some function of x. In that case, suppose this function is x square and this function is minus y square, so this solution will also satisfy the boundary condition, and also this is not in the form of method of separation of variables. So it is not always true that method of separation of variable is only way to find out a solution of given second order partial differential equation or nth order partial differential equation. Now we are going to see it by geometry. Just give me a minute. So you may write a remark. All solutions to partial differential equation are not of the variable of separation form. This is a remark. I am writing the same Dirichlet problem with a very general boundary condition, and you will get to know how the boundary condition is defining that the solution will be of this form. The solution will be the method of separation form. So this was the equation number first, which I wrote in the previous cases. U, what was your u 0 comma y? It was 0. Suppose here I am saying that, say it is g1 of y. Later on you can take it 0. U, x comma and u, and suppose x comma y is lying between 0 to pi. Someone can also write it pi as L. So because this is the boundary, so boundary should be finite domain, is not it? So you can take that length L, or most of the time we take that length L equals to pi. Why we take this length L equals to pi? So there is a reason behind that. It makes this to use this Fourier series. So that's why we are using, most of the time we take the boundary pi. So if even we have L, we try to put that L in the form of pi, so that we can use Fourier series very smoothly. So there is a reason behind everything when we write something, but that is not of our interest. What was d2i in the previous problem? 0. What was f1x in the previous problem? 0.
I don't remember.
And f2x. And this was g of x with z of 0 equals to z of pi equals to 0. So that was the condition. So now here you can see that we have a Laplacian equation and we have 4 boundary conditions. Why it is so? 2 boundary conditions are going to define the constant for u, and 2 boundary conditions are going to define the constant for the derivative of u. So it has u and ux and uxx. So this is needed 2 boundary condition. uy and uyy. This is also needed to boundary condition. So that's why we needed for boundary condition. And here you can see that this is still undefined. We still need to define two more boundary condition. So if we are formulating a single problem, if we are formulating a single problem with only, say, the condition which is defining this is u1, del 2 u1 over del x square plus del 2 u1 over del y square equals to 0 and u1 of 0 comma y equals to 0 and on y equals to 0 y and on the other raised boundary it is 0. On the other boundary just take it 0. So just let's draw the graph. I am formulating 4 questions. This is the x-axis, this is 0, 0, this length is pi, this length is pi. So since it is not uniform, you can ask me, your drawing is so bad. This is pi. So I am taking u1, 0, comma y, equals to u1 0 comma y is equals to g1 y. This is x is 0 on the, what is this? This is y-axis and y-axis x equals to 0. So at x equals to 0 the condition is g1 y. Similarly, I am taking at all the other boundary pi comma y equals to 0 and formulating the 4 model with the given boundary condition, and you will be come up with one model which you have discussed earlier. u1 x comma 0 equals to 0, u1 x comma pi equals to 0. So for this model, what is this boundary condition? u1 pi is varying on this boundary and x is varying on this boundary and y is fixed. And what is y at this boundary? What is y at this boundary?
0.
0. So x is varying and y is 0. So this is 0. Again at this boundary x and y both are varying. Sorry, x is fixed and y is varying. So
0, 2.
yeah, so pi and y, that is again 0. At this boundary x is varying. Yeah, x is I have made, yeah. Sorry. So x is varying, y is fixed. And what is your problems becomes del 2 u1 equals to 0. In the same way, suppose I am taking this boundary condition. Then suppose this is u2. u2 of pi comma y equals to z2 of y, and suppose at the rest boundary it is 0, 0 comma pi is 0, u2 of x comma 0 is 0, u2 of x comma pi is 0, and formulate the model del 2 u2 equals to 0. So this is a separate model, and what kind of geometry it gives. So just del 2 u2 equals to 0. Only the non-zero is u2 pi comma y. So u2 x is fixed pi comma y is varying. So this is u2. If I make a mistake, then please let me know about that. And all the other boundary u2 x comma y equals to 0, u2 0 comma y equals to 0, and u2 x comma 0 equals to 0. In the same fashion, so this I have defined two boundaries. In the same fashion, can we define it for this boundary condition? Suppose this is defining u3 and this is defining u4. Can we do that? So solving this problem with this condition is little bit easier. Suppose we get the solution like u1 x comma y. From here we get the solution u2 x comma y. Using this and all the other 0, we get the solution u3 x comma y, u4 x comma y. And if we know that for a second order ODE, we have two linearly independent solutions, so their linear combination is going to be solution. So since this is second order partial differential equation in two variables, so it may have four linearly independent solutions, and we can see that with this boundary condition. So what will be the total solution of this partial differential equation, the linear combination of them?
Yeah, I think.
So once we solve all four of these problems, the solution to our original system will be of the form, say u x comma y equals to u1 x comma y plus u2 x comma y plus u3 x comma y plus u4 x comma y. Now from here we can see that if we are taking this condition, if we are taking u4 condition, then we are getting the problem which we are solving. Just wait for a minute. Yeah, just wait for a minute. I was checking a mail. Just give me a minute.
Oh, okay. Yeah, no problem.
Just
We
please.
thought that the
Yes, what you were saying? Who was saying? Someone was saying something.
We just thought that it was like an internet malfunction.
Sorry.
We thought that that we didn't hear you because due to internet malfunction.
Okay, no. So because of this reason, we came in the idea that if we are taking the superposition of those functions, then we can write the solution. However, so still we have to stick with whether we are going to take the linear combination of x plus y, or we are taking the product of that separation of variable method. So this is giving just an example, and separation of variable works well with this because as soon as we apply the separation of variable, each of these equations are going to satisfy with these boundaries, so it works well. However, we have to analyze the boundary. If the boundary condition is not of this type, the boundary condition is not of this type with all the function g1, g2, f1, f2 continuous, then in that case, we can't say that we can use the method of separation of variable. So the first thing is that we have to check the boundary. If you are satisfied with the boundary, then you are going to use the method of separation of variable. However, you also have another method. You can take ux equals to v and ui equals to something s, and then you can solve. Yeah, then you can solve this v ux equals to v. So uxx equals to vx, and you can reduce it to the first order partial differential equation, and then you can write it in the form of ut plus a ux equals to 0, and then you can solve this. So there is also a way to solve this partial differential equation, but that is a tricky way, and whether you will be able to find a solution or not. Next, we are going to see the properties of harmonic function. Well,
The properties of what?
Harmonic function. The solution of the
Right.
equation is a harmonic function. So we are going to see the property of the harmonic function, and we are also going to see the maximum minimum principle, mean value theorem. So this is the topic which we will cover tomorrow.